Hello everyone. In today's lecture, we're gonna start a new topic. It's called the kernel trick. Which is also a very popular techniques, either for regression and for smoothing. So recall that when we introduce the regression or support vector machine, we said that even you have the linear discriminant analysis, but you still can have the nonlinear decision boundaries. How do we do that? We can introduce more features. More features. By transforming the current features. For example, we can have the phi, introducing some phi from the current feature space. Suppose we have the D variables, and we can introduce more features like capital D. So here this D is the number of features after featureization, after this phi transformation. So for example, okay, suppose we have one trivial example, the n is 2, okay, and we have also two features. So remember, original design matrix is given by x11, right? So you can think this is the first feature, this is the second feature. Here we have two features, and we have two samples. So and x12, x21, x22, and we have the always including the intercept term. So this is our feature, original feature. Suppose here we only have very small sample size, n equal to 2, but later on you can think this is, suppose in reality maybe you can think of, suppose we can have the like n equal to 100 sample size, we can have the 200 or 50 features or something like that. But here I just give you a demo. What are the phi doing? So for example, if we introduce phi to be the like a polynomial of the order 2, So what's that mean? So that means we not only we introduce we want to introduce, for example, we want to the data to capture the quadratic pattern in the linear regression. So we can introduce more features, right? For example, we can have the x11 square, x12 square. We can also have the first order term, also interaction term. So for example, the x11 times x12, and x1, x2, or x11, x12, and 1. So by doing so, and similarly, we can, for the second sample, we can also do the same thing. For example, x21 square, x22 square, x21, x22, and x21, x22, and 1. So originally our feature space is n by d, right? Small d, which is equals to 2 by 2. But after this transformation, we can have the feature space like a n multiply capital D. So it's, in this case, it's 2 by 6. By doing so, we can even if we have the linear regression, we can have the nonlinear patterns of the data, right? So, but this could give a problem. This technique could give problem. Why is that? So, for example, the degree p polynomials will blow up this d. First issue is degree p. So here we only introduce the degree of the power 2. So this d increased from 2 to 6. Okay. So if you introduce if you want to not only introduce a quadratic pattern, you also want to have the a cubic pattern. Okay, you have more and more terms. For example, the first issue is degree p polynomial blow up this capital D features. Okay. So for example, if for example, if we have the if the D equals to 100. Okay, nowadays it's very easy to find some data set with 100 feature space. Even you want to only consider polynomial equals to 4, this will give us like 4 million features. And this makes the computational difficult. So for example, in a linear regression, if your design matrix is 4 million, okay, if your design matrix is 4 million by 4 million, so that x transpose x is 4 million, and you take the inverse of that huge matrix, is impossible. Even you have the supercomputer, you cannot calculate that big matrix. That is only with 100 dimension and with order 4. So today we're gonna introduce a method. Even we even can have infinite many new features. This is called the kernel trick. So how to solve it? So kernel trick is a key. Okay. So when we can apply this kernel trick, there are some assumptions. If the weight assumptions. So what? Let me rewrite this. What algorithm can we use? When can we use kernel trick? Okay. So first scenario assumption we have is the weight can be written as a linear combination of the training points. Combination of features of training points. Second, and we can use inner products. We can use inner product of this feature function. And do not, we can use inner product without calculate. Without calculate phi x explicitly. So that's the key. That's the key. Because here, this phi x is like a d-dimensional. For example, here, if you in this scenario, this d is 4 million. Okay, so instead, we do not want to calculate the phi over this 4 million dimension vector phi. That's not feasible to calculate. So we're gonna use instead we're gonna calculate the inner product. I will explain in a second what do I mean. Okay, so in this case we can apply the kernel trick. So when the weights can be written as a linear combination of the training points, what's that mean? So weights can be written as the linear combinations of the design matrix features. For example, the X is a design matrix times A can be written as linear combinations I from 1 to n. For each sample point, we have the AI, xi. For A is a vector. A is a vector. A1. Let me write down vertically because vector usually represents a column vector. A1, A2, AN belongs to Rn. And we instead of solving the weight matrix for this d-dimensional weight matrix, we solve this A matrix. A vector. A is only has a size n. Okay. So we try to solve A Rn instead of W in the Rd. So in this case, we assume that d after the transformation, this d is much larger than this n. Okay, for example, in this case, this d is 6. Our sample size is only 2. It's only 2. Okay. Okay, so first, let's see how do we apply this to the regression. So this is the first machine learning tool. We call it kernel ridge regression. Kernel ridge regression. Okay. What we do first, we center. So what's this kernel ridge regression? So think about if we want to apply, for example, even this polynomial of order 4. Okay, think about with order 4, and we have the 100 sample size. How do we apply the kernel regression to this all the transformed features? So first, we center step 1. Center this X and Y. So for each xi, for each feature, we substitute xi by shift by by the average xi minus mu xi. Okay, and then for each I equals to 1 to d, small d. Okay, this is the original how many features in our design matrix. Original data has a small d features, and we centralize this. And also we need to centralize the output labels minus mu y. And our last column in the design matrix usually we give 1, so d plus 1, we assign them 1. Okay, so in other words, our design matrix now looks like x1, xd, and 1 vector. Okay, this is corresponding to the intercept. Recall that the solution for ridge regression the solution is we have closed form solution which is given by x transform x plus lambda times I w is equals to x transform y. So the question here is now if our design matrix is we transformed this, suppose this is phi x, okay, we have large dimensions. The last is still 1, but we have the xd, right? So d is huge. So that we cannot solve this directly, okay? So d is large. If d is large, hard to solve. Okay, that's where we need to use the kernel methods. So what's the kernel methods? So now suppose why this is too hard to solve. You can think this d is much larger than the small n. Okay, suppose the feature is much more than the number of the samples. Okay, so suppose A is a solution. Suppose A is solution 2. So here, instead of solving this equation, we want to find A. Remember, A is in the n-dimensional vector, and x transpose plus lambda I times A equals to y. Okay, if this is the case, if this A is a solution to this normal equation, and recall that if lambda is greater than 0, there is always a solution. Is always a solution. Okay, so then we can have the x transpose. So if we multiply x transpose to each side, okay, we can have the x transpose y equals to x transpose multiply this term x transpose A plus lambda x transpose A. And which equals 2. So now we can take the x transpose A out. We can have the x transpose x plus lambda I. So this lambda is n by n vector, but this one is d by d vector. Okay, be careful here. And times x transpose A. So this implies x transpose A is a solution. So if A is a solution to this equation, we can imply that x transpose A is a solution to original problem, to this equation. Okay, so in other words, we convert solving W. Remember, W is a huge matrix, the capital D, into a problem solving A. And A is much smaller. A is as many as the sample size. Okay, so we call here A is a dual solution. In other words, we want to find A belongs to Rn that minimize x transpose x. X transpose times A minus y plus lambda x transpose A square. Okay, so we convert a problem solving a capital D dimension minimization problem to a minimization over the small n problem. And once we solve A, we can just let W equals to x transpose A. So, and this is this is original, is a solution for original ridge regression. Okay, so in other words, if we can solve this problem, we substitute this, we get a solution for the original ridge regression. And to summarize, when we train the data, the algorithm. So here I just so kernel ridge regression algorithm will equals to, so you train this one, so you solve. Recall, if this is the case, we also have the closed form solution. So solution we want to solve x transpose plus lambda I A equals to y for A. Okay, and once we solve this equation, recall we always have solution for this one, and then your regression function will equals to at any new data point will be W transpose Z. Recall W now is A X transpose A, so it's X transpose A transpose Z, which can be written as A transpose X Z. Okay, so we can return this as a linear combination. So it's a linear combination I from 1 to n AI. So this will be, this X is n times D, right? Capital D. Z is also D. So Z is also transformed space after phi. So this is our training function. So it's so this will be a n by 1 vector. So it's xi transpose z. Okay, so this is our final regression function. And this part is called kernel function. Okay, so we have the so that's what I mean at the beginning of the lecture. We can use the inner product of the phi function. So this is the inner product. So here at k x z equals to x transpose z be the kernel function. Okay, and we'll denote the K to be a matrix, which is equals to X transpose. So X transpose is a kernel matrix, n by n kernel matrix. And we denote each element. So this is n by n, right? N by n. So k n by n, each element inside this matrix we denotes the k ij, which equals to the kernel function. We apply the ith column with jth column. Okay. So the kernel trick here is kernel ridge regression algorithm. So let's summarize the kernel ridge regression algorithm. So instead of original ridge regression, if we transform to get more features, we need to solve this huge matrix. This is the D by D matrix. So think about if this D is 1 million, this will be 1 million by 1 million matrix. Hard to solve. But once we know this kernel function, what we can do is we can solve this k by k matrix for any I and j between 1 to n. So we can solve kij. We can plug in the kernels xi xj. Okay. So instead of solving the original d by d, we solve n by n most features. So this computation takes about because it's n square, right? n square times d. So it takes all time to calculate. Okay. And the second step is once we have the k, we solve k plus lambda times I times a equals to y. We solve this for a. This takes n cubed time. Okay. And for each point, for each new point z in Rd. Okay. Wait. So this is small d. This is no small d. So each new test point, so h z will equals to the solution is given by ai times k xi, all the features, to z. And this step takes about the OND time. The punchline here is kernel ridge algorithm give same solution for original ridge regression. But computation is much faster. For the case when d is greater than n. D is greater than n. Okay, so that's the point. That's the punchline. That's why we use this kernel ridge regression to get the nonlinear patterns by using it gives the same solution, but the computation is much easier. Okay, so next I'm gonna give you a magic part, the kernel trick. So there is a theorem called okay, so we can have the if x and z are two vectors of the n dimension. Okay, then we can rewrite this x transpose z so we can rewrite this phi, the transformed x. So suppose originally we have the only, oh wait, sorry. So this is a d dimensional, sorry. So you can think this is each point is a d-dimensional, and you transform this will this phi x will and phi z will belongs to the huge dimensions. Okay, and the problem is how do we calculate this kernel? So this kernel x transpose phi z. Okay, so think about this. This is a so this will be a D by D matrix, right? D by D matrix. This is a scalar. Sorry, this is a scalar, but this is a vector of the 1 times capital D, right? Suppose you have 1 million, so this is a 1 million vector, and this is a D by 1. So this theorem tells us how to calculate the production of this huge vector calculation. So this can be simply written as the original vector inner product x transpose z plus 1 to the power p. So what's this mean? And this is contains all polynomial terms of degree p. Okay, so I'm not gonna give you proof. I just give you a example. Again, we use the original the example we introduced at the beginning of the lecture. Suppose n is 2, we can have 2 sample. So suppose we only have we want to have our kernel to be we want to have the features of polynomial 2. So we want to have the p equal to 2. Suppose originally we only have the 2 features. Okay, so in other words, if we have the new data point x will be equals to x, we have 1 feature, 2 feature. Okay, and z also we have the z1, z2, 2 features. And let's see, x transpose z plus 1 and the square. So what this gives us? This gives us x1 z1 plus x2 z2 plus 1 square. Sorry. I think we also need to give because design matrix we want to include the coefficient intercept term. So we should have the x1 times z1, x1 times z2, x1 times z2. This one multiply this one, x1 z1, x2 z2, plus plus 1 square. So this, after some algebra, you can calculate this equals to x1 square z1 square plus x2 square z2 square plus 2x1 z1 x2 z2 okay, and plus x1 z1, 2 times x1 z1 plus 2x2 z2 plus 1. Okay, actually this can be written as we can write this as the inner product of the two vectors. So we can have the x1 square, okay, x2 square, square root 2 x1 x2, square root 2 x1, square root 2 x2, and 1. Multiply the column vector z1 square, z2 square, square root 2 z1 z2, square root 2 z1, square root 2 z2, 1. So in other words, we can write this as a vector of the x transpose and z. Okay, so this is the function how we transform the two-dimensional features into the 6-dimensional in this case. So this phi x is a function from the r 2 plus 1, right? It goes to the r 5 plus 1. Okay. So the reason why we do this is that the kernel trick can make we convert. So note, compute phi x transform phi z takes OD time. For example, to calculate this, you just need to calculate the two vectors multiplication of the component wise of the vector and the summation together. So how many features do you have? You need to do the calculation one time. So if you have d features, you just need to do the scalar multiplication d times. However, compute phi x takes capital D time. So therefore, in order you want to calculate this, only takes much smaller time. So this is called kernel trick. So now we can give a little bit summarize. Where can we apply the kernel trick? So to do the ridge regression, you can use these long vectors of the new feature space vectors, right? You can take this much time to calculate. For example, the ridge regression for the with d dimension features. Okay, if you calculate directly, it takes how much time? It's d. So the original ridge regression calculation time takes d to the power cube plus d square times n for training. And for test, it also takes the d-dimensional, okay, which is very time consuming. For large d, okay, for example, d could be 1 million. Okay, and now for the dual trick, for the dual problem to solve A. To solve A, it takes about, it reduces the time from the D to N cube plus N squared times D. And the training takes about N times D time. Okay, and now if we apply the kernel trick, it takes about N cube plus N squared times D, because because this only takes the D time, right? This only takes D time. So, and the calculation here is N small d. Okay, so if we apply the kernel trick, it keeps simplify the calculation a lot, saves time. So in other words, when we apply this kernel ridge regression algorithm, when we calculate this kernel function, we just apply this kernel trick. Instead of calculating this long vector multiplication, we can just apply this kernel trick to save the time to calculate this k. Okay, so that's the kernel tricks for the ridge regression. Okay, and then next I will give you one more example how to apply this kernel trick for the logistic regression, and you will get more ideas. And actually the same trick can be applied to the support vector machine discriminant analysis.